1 2. Mic check. 1 2 1 2 1 2. Iko sawa? Ah. Okay, nakila.
Check, 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 check. Oh my God. Yep. Okay. That's good. Sure. Okay, thank you. So should we start? I'm sorry? Okay. Can you hear me? Yeah.
Maybe you should say that at the end we'll have this test.
Mhm.
So make sure to be there at X time. I don't know. Maybe.
We don't know yet how long it will take, but
Well, yeah. We should say that at the end, just so they are. They don't leave like half.
right. And yeah, okay. That's the only thing I'm supposed to say. Okay, let's start. So today, as I already said yesterday, it's about I/O, input-output, having an effect on the real world. So, excuse me, after today, then you can write programs that actually do things and not just interact with them in the Cabal REPL in the GHCI. So the plan is to recap explicit effects, what we already talked about in the first lecture about Haskell, then show some simple I/O programs, then show you how you can assemble simple I/O programs to bigger I/O programs, and some examples just how to write I/O programs in a functional style. And at the end, after the lecture, we want to write our first test. So hopefully it won't take too long, that we still have an hour for the test. And we will publish it then when it comes to class. Right, so let's talk about Explicit effects again. I mean, this is, I mean, a very cool feature of Haskell, and it would be nice if it had it anyway. But somehow the laziness more or less makes it necessary to have something like explicit effects. Because, I mean, for effects in the real world, it's important, ordering matters, and you want control over when those effects happen. I mean, yeah, makes a difference whether you first read from a file and then write, or the other way around. And the problem with laziness, as we saw, is that it's very difficult to have control over when something gets evaluated, or if it gets evaluated at all. So Haskell didn't really have the option to do what other functional, non-lazy, strict functional programming languages did, that they just have implicit effects. Right. And also we want this equational reasoning, that we can replace one term by its definition, for example, or that we can be sure that the value of one term, I mean, it's always the same. If we call a function with the same arguments, we get the same results. And that would also not go with implicit effects like in other languages. Right. So if Haskell didn't have that, so I mean, let's say we have there is a function getLine, but it has a different type. But if we assume, I mean, in most programming languages, it, for example, would just have type string. And what it would do is it has the effect that it waits for input from the keyboard, and if the user types in a line and presses enter, then that line would be the value of that string. But with what we said earlier, this would be problematic because, I mean, we want this equational reasoning and the referential transparency. So if we had, for example, this program 1, getLine plus getLine, and we, I mean, if it was like this, we would assume that that has the effect of reading a line and then reading another line, and the result would be appending the two. So it would read 2 lines. But because of equational reasoning, program 2 and program 3 would be identical. Because if you substitute getLine for x in this lambda, you get exactly program 1. So by all we have seen this week, program 1 and program 2 should be the same. But if it had this effect, getLine, that it queries the user, then in the first program would query the user twice. So we would enter 2 lines and they would be concatenated, whereas the second one would only query the user once and then it would be duplicated. And similar for the third version, where we turn it around. So these two would have different effects. I mean, again, if you substitute getLine for x and getLine for y, you again end up with the same as in program 1. But here now is the intention that the user enters 2 lines, but then they are concatenated in the other way around. So this would no longer hold that you can do these transformations where you just substitute something. So that's bad because we want this feature. And therefore, it can't work like that. And plus, of course, it's a good idea because we see from the types whether a program has side effects or not. And in principle, we could even, I mean, Haskell doesn't do that, but it would be possible to have it more fine-grained, that we know it does whatever file I/O or only file I/O, but doesn't use the network or things like that. And it, I mean, as we will see, it encourages a style where you keep the I/O isolated to the, I mean, as far as possible, and most of the program doesn't mention I/O. And it makes, and that in turn makes it much easier to test programs because your I/O is concentrated, and then most of the parts are just pure functions, and pure functions are far easier to test because of this thing of the purity, because same input, same output, so you only have to test a function once for a given input. As we will see next week on Monday, I think, or Tuesday, we will talk about testing, which is very cool in Haskell, yeah?
Just a question about that. So does this imply that when designing my program, I should ideally separate the logic which should be pure, and anything else that does include
Yes, yes, exactly. Ideally, yes.
and testing both components. Like, is there a bias towards testing the pure function? Or
Yes, I mean, it's easier, much easier to test pure functions. It's also possible to test I/O, but I mean, normally the ideal Haskell program, all the, as you say, all the business logic, all the logic would be in a pure function, so you test that, and the I/O would be so simple that you ideally don't even need to test it. Right. And the way, I mean, I think I briefly mentioned that on Monday already, but the way Haskell does it, it introduces a type constructor I/O. So I/O takes, like maybe or list takes one type argument. So we could have I/O int or I/O string or I/O bool. And the constructors are not exposed. So it's an abstract type, it's an opaque type. So there's some magic going on. And as I also already mentioned, how you should think of something of type IOA is a plan that would result, I mean, that if you execute the plan, it would eventually result in an A. But so evaluating it just means evaluating the plan. And only execution would trigger actual effects, but you can't, from inside Haskell, trigger execution. And that keeps the purity. So, I mean, one way to think of it is like a recipe, a cake recipe or something. So the recipe is like a pure value, it's fixed, it's fully deterministic. But if you actually execute the recipe, then the outcome, the cake, depends on the quality of eggs in your fridge and so on. But the recipe itself is like a pure thing. And there are two ways to actually execute an I/O action, so-called, right, yes. So maybe let me briefly skip this slide. There's a type very important in Haskell that we haven't seen yet, and it's called the unit type, but it's written like an empty pair, so brackets without anything in it. And both the type and it is a type that has exactly one constructor without arguments, so it has exactly one value. And the value is also written like this with the opening, closing parentheses. And it's called, I mean, pronounced unit. So it's similar maybe to void in other programming languages. Because there's only one value, the value itself is not interesting. If you have a function that has a return type of unit, it would be boring because there's only one possible outcome of this function, namely unit. But it becomes more useful if we pair it with I/O. So an I/O unit is a plan that, when executed, will perform or could potentially perform effects in the real world, but in the end there's no interesting result. So that is similar to like some function, void function in C or in Java or so. A procedure that does stuff but doesn't have an interesting result. And if you want an executable, I mean a program that you can actually run, then I'll show you now. But you will have a main module in your program, and in the main module there will be a main function with the signature I/O unit. And then when you execute the program, this plan will actually be executed. So we can see, I did the cabal init again that I showed you yesterday, but this time I said I want a library and an executable. And so this executable is in directory app. There's a file main.hs, and at the moment, so it's module main, and you can leave that out, by the way. In the case of the main module, you don't need this header, so I could also delete this. And it has an I/O action. In this case, this is the I/O action that will print the string hello Haskell with a new line afterwards onto the console. So we can try this, I hope. So let's try cabal build. Sorry, I wasn't in the right directory. So let's do a Cabal build again. So it builds, and I can actually execute it with, if I want, I mean, I could install, I mean, really compile it to an executable, but I can also, without doing that, using Cabal, I can do Cabal run and the name of that executable. In my case, as we see in the Cabal file, it's called IO. So I can do Cabal run IO, and then it indeed, maybe I should make it a bit larger, indeed prints hello Haskell onto the console. So that's the first program we have seen that actually has an effect on the real world. It changes my screen. Okay. And this thing, this IO action, is the only thing that gets actually executed in a Haskell program. Only this main function, and it must have this signature, IO unit. And okay, I mentioned this. And there's a second way to execute it, and that IO actions, and that is from within the REPL. So there is indeed something called getLine in Haskell. So we can now do Cabal REPL. Let's load this module. That's empty at the moment. There's nothing in it. And so I can ask for the type of getLine. And it's of type IO string. So that means it's a plan that when executed will eventually result in a string. And in the case of getLine, the plan says wait for user input from the keyboard. So if I now, so I could do this in my IO main, but I can also do that immediately from GHCI. So if I do getLine here and press enter, then GHCI will execute it. So in this case, it waits now for input from me. And I can say hello Nairobi and press enter. And then it returns, and this is the result. So this is the string. So the plan has been executed and has resulted in a string, namely the string hello Nairobi. Right, and GHCI behaves a little bit like inconsistent. So in this case, it gave me the resulting string. But if I have something of type IO unit, it will not give me the resulting unit. So if I do put string line, if we ask for the type of put string line, so that takes a string and results in IO action with unit result. So given a string, it will result in a plan, and the plan, when executed, may perform side effects, but will only return unit. And in the case of put string line, the effect that will be performed is printing the given string onto the console, onto the terminal. And if I do this, so if I in GHCI do put string line, hello Nairobi, then we get the effect, so it does print it, but we don't get this unit, the result of the action. So that's a like specialty of GHCI. It doesn't, in the case of IO unit, it doesn't print the unit. But in the case of IO string, it prints the string. So yeah, that's how GHCI works. Right, so here's another example, another useful function, write file. So we can try this out as well. So if we ask for the signature, takes a file path and the string, and the result is a plan, again, without an eventual result. It's just a plan to perform actions when executed. And in this case of write file, as the name suggests, it will write the given string to the file at the given path, or create the file if it's not, or I think it will overwrite it. If it's already there, it will delete it and overwrite it. And file path, we haven't seen yet, I think. So we can ask for information, and it's just a synonym for string. So I can try this out. So at the moment there is, so let's see. So I can, for example, do write file test.txt hello Nairobi, whatever. How are you? Nothing is displayed here. So the side effect doesn't involve the screen in this case. And the unit result type is not shown. But we see here, hopefully we see, yes. So this test.text appeared in my Explorer. And when I open it, there's indeed the 2 lines in that I wrote to it. So I can have an effect on the file system as well. Delete this again. Right, so far so good. And there are like a bunch of primitives. I mean, there is, as we saw, put string line. There's also put string without the final new line. There's put character, I mean, put char character to put a single character onto the screen. Then there is get line, as we saw. There's also get char for to read a single character from the console. And then we saw there's write file, there's also read file, and I mean, there's a bunch of stuff what you would expect. But I mean, this is just single things, like single effects, very simple plans. They do one thing. So the question, of course, is if we want to write a real program, how do we do more complicated things? So you must somehow be able to combine these primitive I/O actions to more complicated I/O actions if we want to write an actual program. And that's what we will look at next, constructing larger plans. So maybe the simplest one is sequencing. So there's this greater than operator, which probably pronounced sequence. Or then maybe is a good. This is actually again something one could call Haskell semicolon, because that behaves a lot like a semicolon in an imperative language. So this will, it gets 2 plans, one resulting in A, one in a B, and it will construct a new plan resulting in a B, and this new plan will perform all the effects from the first plan, get the A result, forget the A result, then perform all the effects from the second plan, and keep that result and return it. So we can try this out. So for example, we could do, I don't know, getLine, and sequence that with put string line Kenya. We can ask for the type. So what should the type be? GetLine has type IO string, and put string line Kenya has type IO unit. So it should result in an IO unit, which it does. So let's execute that in the GHCI. And now it waits, because now it performs the effect of getLine, which waits for input from me. So I can type anything. And now it ignores this, what I typed, and prints Kenya to the screen. Which, of course, is a stupid example, but nevertheless. I mean, it's more useful, for example, with put string line. I could do put string line, or put string, hello, and then put string line Kenya. And now it will perform both effects in sequence. First the hello, then the Kenya. So that's sequencing. That's basically what, as I said, what a semicolon does in imperative programming. You have a bunch of statements, and one is executed after the other. Right. So here's another example. I mean, get 2 lines, so it would do 2 get lines, but because of the fact that the sequencing operator forgets the result of the first one would be ignored. So we can do this if we like. Get 2 lines, type IO string, get 2 lines, get line sequenced with get line. If I reload and execute this, then it waits. So it now performs the effect of the first get line. So I can enter something. And now it performs the effect of the second get line. and it just returns the result of the second get line and ignores the result of the first get line. Right, so that's basic sequencing of I/O actions. I mean, sometimes we call that action. If something in I/O, sometimes a synonym for that is, I mean, you could of course say value in I/O or I/O value, but I often say I/O action. But keep in mind, it doesn't act until only if it's in the main function of the main module and you execute the program, or if you do it in GHCI. Right. So this is one thing, so you can sequence. Another thing is you can modify the result. So given a function from A to B and an I/O action of type A, you turn it into an I/O action of type B. So how does that work? It will first execute the side effects of the given action, which will result in an A. And then before returning, it will apply the function to the A to get a B, and that's then the B that it returns. So it will be the same side effects as in the given action, but it will modify the result. So for example, we can define this duplicate line thing. IO string. So we lift m, function that takes a string and duplicates it by concatenating it to itself, and get line. And I think lift m, no, I don't think. Is it right? Yes, I have to. So this is not in the prelude, so I have to import control monad. So let's try this out. So now it performs the effect of waiting for my input. So if I now say Kenya, so now this original action, the get line, would result in the string Kenya, but now before it's returned, it will apply the given function to it. So now I get Kenya, Kenya. And there was this hint, and that's I think not in the slide, but I wanted to mention that anyway. If we ask for information on I/O, then there is lots of intimidating stuff that's not important. But in particular, we see that I/O is an instance of functor, which we explained yesterday. And also, if you look at the signature, that's exactly the signature of fmap. And indeed, lift m is just the fmap for I/O. So instead of using lift m, I could just use fmap. So I can remove this here again. And I could use fmap. Or I can use the nice operator we learned yesterday, like so. And that will be the same thing. So I can do this again. And that's the same thing. So I never use lift m, I always use fmap or the dollar. Right. And another example, so we want to shout, right. So we could do, I mean, let me import this. I can also do this properly. So data.character to upper. Now I can do shout. So there are now two fmaps involved. Map is also an fmap. So getLine results in a string, which is a list of characters. So now to this string, I apply the function after executing the plan, map to upper. And to upper turns a single character into its uppercase version. So map will apply this operation to a whole string. So it has the effect of turning the whole, making the whole string uppercase. So I can sound like Donald Trump tweeting. Shout. If I now do Nairobi, it will return the string with all caps. Right. Any questions at this point? Yes?
I don't understand how FMAP is still working with IO.
FMAP is a method of a type class. So it works for all instances of, I mean, it's a method of the functor class. So there's a type class functor. Sorry. That we looked at yesterday. And it has this fmap method. And every instance of functor has this, I mean, for every instance you can use it. And I mean, yesterday we had examples lists and maybe and tree. So for all of those we could use fmap. And now I just showed you that, or we can also see this here, that IO is also an instance. So for every instance of fmap or functor you can use fmap. That's the point of making it an instance. So it sometimes has individual names, as we saw. I mean, for list it's called map, and for maybe map no, I think not. But anyway, for IO it's called liftm, but we can also use fmap. Can just uniformly for all functors we can always call it, I mean, use fmap.
So is there a preference between?
I prefer fmap. Because, I mean, then you don't have to learn all these individual names for the individual fmaps in different types. But sometimes, I mean, for example, here I use map and not fmap. So, but this, I mean, I could just as well have used fmap. But then maybe it's a bit confusing because there are two fmaps. So one is for the IO functor and the other is for the list functor. So therefore, I'm trying to make it clearer that this is the one for lists. So it's again a matter of style. Better, I mean, and map is also shorter than fmap. So normally I mean, by default I use fmap, but in special cases like now, sometimes I use map. Right. Any other questions?
The result type.
I'm sorry?
Like the result type, does it have to be shorter?
Does it have to be what?
Showable.
If I want to execute it in GHGI, then yes, because GHGI will try to. So for example, if I change this to foo IO, let's say string to string, that's right. Let me do this explicitly. Okay, I don't have to do this explicitly. Fine. So this is a perfectly well-defined I/O action that also compiles. I mean, the compiler accepts it. So what that would do would be, if you execute it, it would wait for user input and then return the function that will prepend the given user input to a string. But because functions are not showable, if I now do foo in the REPL, okay, I didn't know that. I would have expected it complaints immediately. But if I now do Nairobi, something's wrong. Hang on.
Maybe run it outside GHCI because it has tons of magic there.
Yes, but this is very strange. Okay, but it doesn't. Okay, fine. And so I was wrong. So it does. I mean, you can do it in GHCI, but it just doesn't show you the result.
Well,
So,
in general, like, financial GCI, it was not for.
I mean, you can, if you, as I said before, there are only two ways to execute an IO action. One is in GHCI and the other is the main function of your program, which always needs the unit return type. So basically that question doesn't make sense. In between, I mean, if we will see later when we build larger IO programs, I mean, something like foo might make perfect sense. But in the end, when you eventually execute it, it will always have unit return type. So this question doesn't appear.
Yeah, maybe we can show the main or at the end, or when is it?
Yes.
Like we could put another function that is not part of main, so there's like never gets executed.
So
To show that that function like,
does not
that
get
side effect doesn't get executed. Yeah.
sure. I mean, I could define this thing. I mean, also in main. I mean, if I had this foo defined here, I mean, that's perfectly legitimate. But it will be completely ignored. I mean, the only thing that's executed is the main. And of course, somehow in main, I could make use of foo somehow. But in the end, the only thing that's executed is main, and main is of type IO unit. So the question, I mean, the only time where you potentially could execute something that doesn't, an IO action with a non-unit return type, would be in GHCI. And I was wrong, I thought it would refuse to do it, but it seems it just, in this case, if it's not showable, it just doesn't show you the result. Okay.
If it's unit, it doesn't matter what comes in white, it just goes unit.
Mm-hmm.
But so it doesn't matter if it's how much limit program to go to unit.
Right. Yes. Other questions? Okay. So then there's another thing called lift M2 that now takes a function with two arguments in curried form, A to B to C, and you have two planes, one with return type A, one with return type B, and it combines them to a new plane with return type C, and I hope at this point you can guess what that will do. So this new plane will first perform the side effects of the first plane and will get an A, will remember the A. Then it will perform the side effects of the second plane and get a B and remember the B. And then it will plug the A and the B into the given function and get a C and return this. So earlier we were not able to, I mean, we did this getLine sequence, or getLine then getLine, and then the result of the first getLine was ignored because that's how sequencing works. Now we can write this join two lines which will indeed ask for two lines and then not forget the result of the first one, but concatenate it with the second one. So let's try this. Join two lines, IO string. Wrong terminal. Sorry. Okay, and this I must import. Yeah. So this, if you use Visual Studio Code, then you can. And here, yesterday we talked about import options, and we said that you could import a whole module or just explicitly what you need. And actually, the Visual Studio. I mean, first of all, you see that this lift M2 is defined in many modules. And we also see that it gives me the options to import the whole thing or just explicitly that one. And as I said yesterday, I think it's better in general to do it explicitly. And now it has added automatically the line here. And I have this formatter, stylish Haskell, I think. So if I save, then it gets nicely aligned. Okay. Let's reload. Try this, join two lines. So now it's performing the side effects of the first get line. So I can say hello. And now it's performing the side effects of the second get line. And now it's applying the given function, in this case plus plus, to the two results. And that is then the overall result of this. Right. Okay, this is just another example. So I could and I can be fancy and just do flip. I think on the slides it's more explicit. So if I do flip two lines and do hello and Kenya again, then it now also concatenates them, but the other way around. Okay. Right, and now we can basically fix these, or we could fix these things in the beginning. Do that properly. So, the intention, when we didn't know better, our intention was to read two lines and concatenate them. So that's exactly this join two lines that I just wrote. And this thing would duplicate one line. I think we have that already. Not sure. Do we have duplicate line already? Maybe not. Yes. That we have already written. And flip we also have. So now basically we can do these things properly without sacrificing referential transparency. Right, and so far it's already quite cool. So we can, we have our primitive actions, we can sequence them, and we can modify the results, and we can even combine the results of two actions. But one thing we can't yet do is to make the action or the later action depend on the result of an earlier action. So in the case of lift M2, the side effects are always like statically known when you write this. You will execute the side effects of the first action and then the side effects of the second action, no matter what the result of the first action is. Later in the final result, the result of the first action is used, so it's not dropped like in sequencing, but the action, the side effects themselves don't depend on whatever the outcome of the first one is. But of course, we want programs where it depends on that. You want to, for example, read a string, and then depending on what that string is, do different things. And this is, of course, possible in Haskell. And that is this funny operator. So it looks a bit like the sequencing one, but then it has an equal sign afterwards. And it's pronounced bind, because we bind two actions together. So what that will do, so it's a bit similar to sequencing, but for sequencing we had like an IOB here. So now it's a function from A to IOB. So what this will do is it executes this, when it's executed, so it will result in a plan that when executed will first execute the side effects of this action, and A will result from that. Then this A that comes out of this will be plugged into this function, so this function will apply to the A, to the result of the first action. Out comes a plan of type IOB, and then those side effects will be performed, and the final result B is the overall result of the computation. So you bind these two things together. And because it's a function, what this IOB here can depend on the result of the first one. So you can do different things depending on what the first action results in. So this is extremely important operator in Haskell. But it's also in principle, all you need to understand is this one. So all the others we have seen so far can be implemented in terms of this one. So they are all just special cases. So let's see examples. So we had this shout where we transformed the result of getLine. But now we want to use that result and print it to the screen. So shout back. Is that, yes. So let's first try it out and then think about why it works. So I execute shout back in the GHCI. So now I can, for example, type Kenya. And now it prints the uppercase version to the screen. So let's try to understand this. So this is, I think, best. So in order to apply bind, we first need an IO action. That's our shout. So that reads from the keyboard, and the result is mapping to upper over whatever the user entered. So our A of the bind is string in this case. So now we need, and because this shout back has unit return type, here we need something of type string to IO unit. But put string line has exactly the right type. It takes a string, prints it to the screen, and doesn't return anything, or returns unit. So this fits the bind. So we can indeed bind put string line to shout. And the overall thing has type IO unit. And again, so what it does, first it performs the effects of getLine, waits for user input, then out comes a string. That string, this function is applied to it, so it's turned into all uppercase. And then it's applied to, this function is applied to the resulting string. And then the result will be an IO plan that prints the string to. So I can do this with, so I start again with shout and bind. But now because I want to do it twice, I can't just use put string line. Now I need a name for the result of this. And this is where lambda comes in handy. So now I can do put string line x and again put string line x. So I'm using this sequencing here because put string line doesn't return an interesting result anyway. So we can, using this bind and sequence, we can string several IO actions together. And it's also called bind because I can now bind this variable name x to the result of this. So this will perform shout. I bind x to the result of this. Then I perform this action, which will print x to the screen, and then I will do it again. So let's see whether it works. Shout back twice. And it does do that. Just see what the next example is. Right, and one final important operator is missing, and that's called return. It takes an A and produces an IOA, and that is the plan that will not perform any side effects and just return the given A, which also shows that IO, if something has type IO, it doesn't mean it will perform side effects, it just means it is allowed to perform side effects if you execute it. Whereas if something doesn't have an IO in its type, then it's not allowed to perform any side effects. So IOA means we may use effects to produce an A, but we don't have to. And A says we must not use effects to obtain an A. Right. And with this, with return and bind, you can do everything else. And there is no way to get out of IO again. So once you have IO, something with IO, then everything you can do will always result in another IO. So once you have basically polluted your code with dirty side effects, you can never get rid of it again. Except you can, we already mentioned this unsafe perform IO. We already said that it's called unsafe for a reason and one shouldn't use it, but it is there for library authors and so on. Because sometimes it makes sense, but normally not. In your everyday life as a Haskell programmer, you will never need to use that. Right. And a way, if you think about it like that, so IO basically marks dirty side affecting code. And one way to think of bind is that it temporarily does allow you to get to it. So basically, because in this function here, you do have an A, but it's only temporarily, because after the bind, it's again wrapped in IO. So people have written millions of tutorials about this thing. And one image is this box. So you can think of IO as like a box with an A in it. And then this bind allows you to basically temporarily peek into the box, look at the A, but in the end you have to wrap everything into a box again. Okay. And now we could implement the other functions we have seen in terms of bind. So the first way to make, is that all? Let's see. I can probably hide it from Prelude. So this was the sequencing operator. The then was the first one we used to combine primitive IO actions to more complicated ones. And I said all you need to understand is return and bind. So we can implement the sequencing operator in terms of bind. So it's just we bind, we perform the first action, and then we get A as a result, and we perform the second action and completely ignore the A. And then it complains that I'm not using the A, and what does it else? Yeah, so it gives me the hint that what I'm defining, I should use it. And one could alternatively write this here as, this is exactly const. So I could write this as const y. So the sequencing operator is just a bind where I don't make use of the bound value. So it's just a special case where the second action does not depend on the result of the first action. And similarly, lift m. So let me import it again. No, let's not. I can just implement it. Sorry, it's not. So this lift m, so the f map for IO. So given function from A to B and an IOA to do to get an IOB fx. I can also implement in terms of bind. So I do x. Now I bind the result, which is of type A, and I return FA.
The bind has double equals.
I'm sorry, what?
The line 30, you have double equals.
Oh, yeah, sorry. Thank you. Right. Okay, so this is exactly what liftm does, or fmap. So you can define that in terms of return and bind as well. And finally, the liftm2. So let's again not import it. So we can also define that in terms of return and bind. So given a function f and an x and a y, I can execute x. The result is of type A. I bind it to variable A. Then I perform y, do another bind to get the result b, and then I return f applied to A and B. So that's the liftm2. And right. And this looks a bit like, sorry. Right, this looks a bit confusing maybe. So let's format that differently. So this already looks nicer somehow. And because this is so important in Haskell, and as we will see next week, it's not even only used for I/O, it's used in many other contexts as well. So it's all over the place. And this gets a bit messy. Haskell has special notation for this, so special syntax. So one could write this.
Maybe we should leave that.
Yes, and define a second. So what you can alternatively do is have a so-called do block. So it starts with do, and then it must be indented, which in this case it is. And then instead of writing this, you can write the following. Yeah, yeah. Right. Let me just show you both. So this is exactly the same. I mean, it's just syntactic sugar. So I think, before it even gets to the compiler changes this version into that version. It's just because it's easier to read. So there's this do block, and then instead of using the bind, you can use the, this reverse arrow. And there's like two more things, syntactic things that you can do. For example, maybe the shout back twice. We could first format that differently. So here, we use bind in the first, but for the second thing, we don't need the result. So after what we have learned so far, we could rewrite this using do notation as follows. So instead of this, I bind x to the result of shout. Then I bind something I'm not interested in to the result of put string line. Yeah, no, sorry. Yes. Anyway, I can do it like this. So if I'm not interested in the result of something, I don't have to bind it against a variable. I can just write the thing. So this would be equivalent to shout back twice if you use do notation. And that is also a matter of taste and style, whether you use do notation or not. So it's completely equivalent. There's no performance impact or anything like that. Normally people would, for very short things like this shout back, probably not use do notation. But we can, of course, just to practice this, do it. So if you wanted to write this in do notation, would be do. We shout, bind the result to x, and then do put string line x. So in this case, probably people would prefer this version with the explicit bind because it's shorter and compact. But for like longer things, normally people use do notation. But there is no hard and fast rule. Right. And there's one final thing, one final syntactic sugar in do regarding let blocks. So let's look at that. So this is a bit bigger example. So let me see whether I can reproduce this. Okay, so first it prints what's your name on the screen. And I mean, put string line doesn't have an interesting result type, so I can use the simple sequencing. Then it waits for a line from the user. And now I am interested in the value of this, so I bind it to a variable named name. Okay. Now I can, for example, say, sorry. Is it like this? Yeah. Okay. So now I print where do you live? Get line. I don't want to forget this, so I call it log for location. Now I use a let. So guard. So I want to do give different answers depending on where you live. So if log is Nairobi, fantastic. And if it's Nakuru, is that a city in Kenya?
Yes, yes.
Okay. Okay. In so this is now like a IO action with lots of primitives. So we have 1, 2, 3, 4, 5, 6 primitives that we somehow bind together. So let's first try it out. So it prints what's your name. I say Lars. Where do you live? Regensburg. Never heard of it. And if I now say Anderson, Nairobi, that's fantastic. So it works. So it's a little program that actually does stuff and also like interactively. And now we can like convert that to do notation. So the point is you wouldn't need do notation. I mean, especially if you format it nicely, it basically doesn't really matter. It's not much more readable or anything, but a little bit because you get rid of some clutter. So using do notation, we are not interested in the result of put string line, but we are interested in the result of get line, of the first get line, and we wanted to call it name. So then again, we are not interested in this, in the result, because we just perform this for the side effect, not for the result. Ditto here. This one we want to call location. So we bind the result of that against location. And now the final thing that you can do in do notation that you can't do in regular Haskell, you don't need this in. So we can just change this to this, for example, and remove the in and put this like this. So lets are cleaner somehow, or shorter. And if we do this and do the greeting prime, it should do the same. Right. So it works as before. It's exactly equivalent. As I said, not even sure the compiler, the parser maybe even, or some preprocessor of the Haskell will convert this do notation into exactly this. So it's, yes?
There are some questions in the live.
Yes?
In YouTube or
Okay. On line 64, is the exclamation supposed to be a string? Can you also repeat one?
Can I also do what?
Repeat one. Repeat once. Sorry.
Can I also do what?
On line
Yeah,
64,
yes, that's, yes.
is exclamation.
Yes.
Supposed to be a string?
Yes.
Can you also repeat on? Okay. Instead on concatenation in this same line, why not just put in there at once?
I think maybe he's asking about placing the name variables inside.
I mean,
string.
first of all, it is a string, yes. And but I'm not sure what he means by.
Like in Python and JavaScript.
Yeah, string interpolation. So there's no built-in string interpolation in Haskell. I mean, there are libraries that do that with like template Haskell and stuff. But there's no good or no built-in string interpolation. So you have to do it like this. And I mean, I can't just use characters because then it wouldn't type check, right? Because I can't concatenate a string with a character. I mean, the plus plus takes two strings. Therefore, I need to use double quotes, and that's a string. But of course, I could do 2 exclamation points. I mean, any string. Are there other questions? Because I think then we should have a break now.
So, what makes the bind and the return special?
Sorry, what was the first part of the question?
What makes bind special? Like, why does it? In the
Oh,
in the original examples, when you are doing the dash line twice, it didn't work. But then magically when you did dash and 2 and 1, it worked. So what makes? What's the difference?
I mean, bind is just. I mean, it's special because it's so powerful, but I mean, no, I mean, it's not as if it didn't work before. It's just, I mean, depends what you mean by, I mean, it worked exactly as intended, and the intention of the then is to forget the result of the first one. I mean, it was just not the right tool for the job. If we wanted to remember it, I mean, we needed to use bind. So it's not as if it, I mean, there's nothing wrong with then, with the sequencing operator. It's just not, I mean, depends on what you want. Sometimes you don't need the result of the first action. So there's nothing special about bind. I mean, or you could say it's very special. I mean, that's the magic of I/O, that you have this bind. So as soon as you have return and bind, you can write any program you want in I/O. And it's just, I mean, the genius of Phil Wotler was to recognize that once you have that, you can do everything. I mean, you can build arbitrarily complex I/O programs together, just having return and bind. And then people realize that often you don't need the full power of bind. You can ignore the result of the first action, so they defined this sequencing operator which forgets it. And lift M and lift M2, and because those are all special cases that appear frequently. But the point is just that return and bind are so powerful that any program you want to write, you can write with those two. And I mean, yeah, it's special that that exists, but somehow people manage to make it happen.
But it's not. Eventually, we will learn how to define those ourselves, and you will see that there's no magic inside. It's just in this case.
But for I/O, it's magic.
I/O is magic because it interacts with the external world. So GHC handles that for you. But once we start defining our own to deal with our own source code without interacting with the external world, you will see that it's not like magic. It's just hidden code.
Other questions? Yes, Anderson?
You abstract away your code so it doesn't clutter all over.
There's someone who was asking why use lift ends and not the fast approach, which seems to be more simpler.
And not?
The fast approach. I think those are two best approaches that are using the lift ends.
Where did I use lift M? I think I never used it anywhere.
I think it's lift M to
That's the
I mean, I don't use lift M, right? I used fmap instead, or the dollar.
With it, right? With it, I mean, we use it in the before changing it to fmap.
Yeah, I mean, I personally never use lift M. Some people, especially old school, I think they like it, but I never use lift M. I always use fmap or the dollar thing, in the case of I/O at least.
I think that might be the question, or he's asking about why we have to go over this. Like, you already explained this, but maybe why we have to go over all this extra machinery, because the first two slides were so simple without any lift them, and now we have to lift everything to I/O. So like basically the meaning, the why having explicit side effects.
Maybe, but I hope that was clear from the referential transparency thing.
Yeah.
So maybe we should just wait for clarification of the question. Are there any other questions? Okay, then let's have a short break. 10 minutes or so, because I think the next topic, right, is to have some examples that are more, I mean, to build some like cooler programs. So this was basically all you need to know about I/O in principle. So now it's just examples.
Yeah.
should I wait or?
If however you want, I'm just letting you know.
Yeah.
I will open the chat here to make sure.
Okay. Should we continue? Sure, we can. Yeah. No rush. It's fine. Should we continue? Okay. Then let's start again. Right. So now, as I said, just some examples and also showing that basically what applies to functional programming in general also applies to I/O. But before we come to that, I wanted to make two remarks. First remark is that this is a lot like it looks a lot like an imperative program. So it's like an imperative, like part of Haskell. And Simon Peyton-Jones, he who said Haskell is useless, also said that Haskell is the best imperative programming language. So normally, of course, we write functional programs, but if you want to be imperative, you can, and it's nice. And the second remark is that I want to make, that's not on the slides actually, is that return is maybe a bit unfortunate, the name. Incidentally, there's another name for it, pure, which might maybe be less confusing. So those of you that are used to like other programming languages probably associate with return that it somehow it stops execution at that point and returns a result, but that's not the case in Haskell. So for example, I could have a return somewhere there in the middle and it just wouldn't do anything. So it has nothing to do with, return has nothing to do with a control flow. It doesn't mean it stops execution and exits the function or whatever. It just means what I said it means, that it's a plan that doesn't have any side effects. And the result of the plan is the value you return. So in that sense, return is maybe an unfortunate name because it may confuse people that are used to that return, like stops right there and then exits whatever, the do block, or it doesn't. So if I put somewhere there return 42, it wouldn't just have any effect. In particular, it wouldn't stop anything. Right. So as, first of all, we define this helper function that asks a question. So ask. So given a string, it results in an IO string. So the intention is You can specify a question, a string, and then that string will be written to the console, and then the user can enter an answer. So we know how to do this now. So we put it to, and we just do a get line. I think that's it, is it? Yes. So we can try this out. So for example, ask what is your name? So it prints it to the console, and I can say Lars. And the result of the whole thing is then Lars. Okay, so this is just, and now we want to write a function that asks many questions and collects all the answers. So ask many, so it gets a list of strings and returns a list of answers. So ask many. And this is now just a function on lists. So we can just use the standard design pattern on lists. So nothing we have learned so far you now need to forget because we do I/O. So of course it still applies. So we have the case of the empty list, in which case there is just an empty list of answers and we don't need any side effects. So we can use return and just return empty list. In the second case is we have a non-empty list. So we have one question and potentially more questions. So we can get the first answer by using our ask helper function. And we can recursively call ask many on the tail of the list to get the other answers. And we can then return as final list the first answer and the other answers. I should short it X. Right. And we can try this out. So ask many, let's say, what's your name? And where do you live? So, and it collects the answers and returns me the list. So far so good. So the lesson here is, I mean, everything you have learned about writing functions on lists still applies to I/O. So function on list, normally you have two cases, the empty list case and the non-empty list case. And as before, I mean, we could also do this as a fold right, I suppose. Yes, if we wanted to. But in this case, probably one wouldn't because this is relatively complicated, the function. So this looks nicer. But it feels a lot like a map. I mean, what we do is, I mean, we have a list of strings. And in principle, what we do here is we apply this ask function we wrote earlier to each element of the list. So, I mean, one might be tempted to instead do this. Right? I mean, it feels like it. But if you think about it, that has the wrong type. Because map takes, I mean, yeah, map takes a list of something, in our case in our case strings, a list of strings, and a function from string to something else, in our ask in our case, which goes from string to IO string, and then it turns the list of A's into a list of B's. So it turns the list of strings into a list of IO strings, which is not the same as an IO of a list of strings. So this has the wrong type because it has type string to list of IO strings. So it's important to realize that that's different. IO list of string is a plan that when executed will in the end result in a list of strings. Whereas this is a list of plans where each plan when executed will result in one string. And that's two different things. I mean, here we have one plan, here we have many plans. But we can easily make that work by writing a function that takes something like this, a list of IO actions, and turns them into one IO action with the result list. And that's called sequence. And that's probably in scope. Yes, so let's hide it. So let's define it here. So if we often have this situation, so we have a list of IO actions and we want to turn it into one IO action where we collect all the results, the individual A's, into a list. And this is very similar to what we did here. So again, it's a function on lists. So for the empty list, there is just the empty list to return. And if we have a non-empty list, we ask for the result, we bind the result of the first action, and we recursively bind the result of, sequence access. So we call sequence recursively on the tail. So we get the ys is now all the results of the tail, and then we return ys. And once we have this, we can write ask many like so. And so much shorter and nicer. And it should work again, still work, of course. Right. And there's also a variant like of map, because this combination, first map and then sequence, is very common. So there's also something called map M. Why it's not called map IO will become clear later. So, So map M looks very similar to map, hence the name. The only difference is instead of having something from A to B, we have something from A to IOB. And then given a list of A's, it will give us IO list of B's. So that's different to map for the same reason. If we used map, then we would get a list of IOBs and not an IO list of B's. But it's very similar, and now with what we have done, we can simply write it like this. So it's just the usual map, and then we use the sequence we just defined. And with this, we can write this even shorter as map M ask. So it should still do the same thing. And it does. And the point of this is, first of all, to introduce you to the important functions sequence and map M that are often used and very useful. And secondly, to show that what we said about functional programming, often when we see patterns or things that occur often, we abstract that away, like for fold right, fold left prime. We saw yesterday the dot operator. All these useful little tools that they are very polymorphic, can be used in lots of situations. And the same is also true with I/O. So map M is also one of these tools or useful functions like map that often make sense. As we can see, then something, because that's a task that you do often. You have something you want to, like something with a side effect that you want to apply to each element of a list, and then you, where in a pure context you would use map. Now you have this map M to do that with side effects. Right. I think I did all of this. Right. Now a second example, which illuminates a little bit this thing that one should keep as much as possible pure. and also that has advantages. Right. So the idea is we want to basically write like a generic system that can implement something like whatever. If you call like a calling center, and then they say, if you want to talk to manager, press A, press 1. If you want to whatever, press 2. But for binary questions, I mean yes, no questions. So the idea is you can basically define the flow of the conversation, what should happen if the customer or whoever, the user says yes or no, and then there can be follow-up questions, and again yes or no, and eventually maybe there's a result, a string. And we want to implement that. So we start by something that has no I/O ever anywhere, just defining this interaction type. So data interaction. So an interaction can either be a question, which takes a string, that's the question, and then recursively two interactions. So the idea is this represents that the string is the question that is asked, and if the user says, it will be a question that you can answer with yes or no. If the user says yes, you proceed with the first interaction, and if it's no, you proceed with the second one, or the other way around, whatever. And we also see this is another, I mean, it's very similar to our binary tree type. It's a bit different because now it has these strings in the nodes. Our binary trees didn't have any like data in the nodes. Okay, so and then we need a base case. So if there are no more questions, we just answer with some sort of result. So this is a purely functional algebraic data type. I mean, it's a tree type. It has nothing to do with I/O first. But we want, I mean, the idea is that we can now take such an interaction and basically execute it in I/O. And let's define two example interactions that we can then play with afterwards. And I think one is called pick in the slides. So we start with a question. Do you like functional programming? And if the user says yes, we follow up with a second question. Do you like static types? And if the user says yes again, we say result try, I would say try Haskell. I don't know why it's OCaml in the slides. I don't know. And if the user says no to the second one, we want to say try closure. Okay, and if he answers no to whether he likes functional programming, we follow up with the same question. And if he says he does like static types, we say try Rust. And if he doesn't, is it JavaScript, Python? Okay, and I'm sorry, it's the other way around. No, it's not. Oh, sorry, sorry. In the slides, it doesn't ask the same question. It asks dynamic types. Sorry. And then do here Python, and if he says no, then try Rust. Is that right? Yeah. Oh yeah, and I could, of course, derive show, for example. So I mean, this is just a boring old tree. I mean, it's nothing to do with I/O. But the interpretation, I mean, the intention is that we now write a program that will take such a tree and actually execute it as an interaction with the user. And I mean, in functional programming, what you often do, I mean, you do that in other programming languages as well. You try to split your problem into small, manageable parts and useful parts, and then use those to build more complex things. So one thing we obviously need is we need something like this ask function we had before, where we ask a question and then get a yes or no, a Boolean result. I mean, earlier we got like, where do you live or what's your name, a string as a result. Now we want something with a yes, no, for yes, no questions. And what's that called here? Okay, we get to that. Here's a second example. So let's do the second example first. So you are probably all too young to understand the joke in this. I mean, that's called Ford because Henry Ford, I mean, he was the one with the Model T, the first mass-produced car in the world, but it was black. And I mean, there's this funny, or this quote from allegedly Ford, attributed to Ford, where he said, yeah, you can have your car in any color you like, provided the color is black. So we want to model this. So first we say, would you like a car? And we do this, the yes case soon. And in the no case, we immediately stop and say, never mind then. Okay, and if he wants a car, we follow up with, do we like it in black? And if the user says yes, then we say, good for you. But if he doesn't, we just start all over again. So, which is to show that these trees can be infinite. I mean, this is now an infinite tree because it has itself as a subtree. And there's nothing wrong with that in Haskell because it's lazy, so it doesn't evaluate the whole tree. I mean, if I wanted to show it, it would, of course, crash. I mean, if I want to show it, then it doesn't stop. But it's perfectly respectable Haskell value of type interaction. Right, and now we have these two examples, and now we can try to write something that executes that in I/O. And as I said, as an ingredient, we need this ask bool. So we want to, as a helper function, so given a question, it should result in an I/O bool. So do block. So we first present the question to the user. Right. And we just append a yes, no to give a hint. Sorry, no, not in, sorry. Of course, the question is, sorry, right, like this. Then we, okay, now we use this get character that I mentioned that exists. So instead of get line, which waits for a line, this only asks for a character. Then we, just to make it look nicer, we write the empty string. And now we keep it simple, so we just so if the user presses Y, lowercase or capital, then we treat that as true, and if he presses anything else, we treat it as false. Alternatively, of course, we could also have checked for y and n explicitly, and if the user presses something else, we could like loop to until he presses y or n. So let's try this out first. So do you like Haskell? So I get the question with this yn in brackets, and if I now on my keyboard type a y, it returns true. And if on my keyboard I type a whatever t, it returns false. Right. So this is this, and now with that it's easy to write this interaction thing. So let's do this. I just want to check what it's called. Okay, it's called interaction. So interaction takes an interaction and executes it in I/O. Or I mean, it creates a plan that when you execute the plan will execute the interaction. And again, what we have learned about Haskell and algebraic data types and standard design patterns for functions, of course, is still true. In particular, because interaction has these two constructors, result and question, we need two equations. I mean, that's our first thought. And let's start with the easy one, the result one. In this case, we can just show the result and we are done. Is that what he does? Yeah. Okay, and if it's a question, with the question and yes and no branches, we can now use our helper function ask bool to ask the question. And now, I mean, if the user said yes, then we recursively continue with the yes branch, and otherwise we continue with the no branch. And if I wanted to, I could, I'm not sure how it's done in the slides, but also do it like this. And that's it. And now we can try this with our examples. So interaction. What was the first one? Was pick. So do you like functional programming? Yes. Do you like static types? Yes. Try Haskell. And let's do one more. Do you like functional programming? No. Do you like dynamic types? Yes. Try Python. So that works. And now we can also do the Fort thing, which again, Fort is an infinite tree, but there's no problem with that because we are in Haskell. So would you like a car? Yes. Do you like it in black? No, I want a red one. So it just now loops, and again, would you like a car? I say yes. Do you like it in black? No, I want a red one. And would you like a car? Yes. Do you like it in black? Okay, fine. Good for you. So this works perfectly fine, and it can even model like infinite interactions, as you saw. So there's no problem that it's an infinite tree. Right, but what we can also do, because our interaction type is just a pure value, pure pure Haskell value, no I/O inside, we can also write a pure interpreter for interactions, which, for example, we could use for testing with no I/O anywhere. So we can, I don't know what it's called, simulate. So we can simulate an interaction. And now, instead of using I/O to get answers from the user, we just hand in a list of Booleans already. So the idea is, first question will be answered by the first Boolean in the list, second question, second Boolean, and so on. But of course, the list might be too short, so we can't return a string. We return a maybe string. And now, again, standard design pattern. So in the result case, we don't care about the answers that may still be in this list. If we just return, just the result. And in the question case, yeah, now I have choices. I mean, I could do a case. Have we officially introduced case already at some point?
Yeah.
Yeah. I mean, I now need to know whether the list of, whether the booleans are empty or not. So, I mean, one option would be to do a case, I mean, I need a name for this, of course. Let's say answers. Case answers of, and then go on. But I can also just do more cases. And I can even do the yes and the no case like separately. So one thing I can do is, I mean, the question is completely irrelevant in this case because it's not presented to the user anyway. So, and for example, if the list starts with true, so then it's the so I just recursively continue with, sorry, I must give this a name. It's called B's for booleans. So I have used my first boolean and pass on the rest. So now for the no case, can do the same thing. And finally, if the list is empty, I'm stuck. So I just say nothing. I mean, the result is nothing. Why is complaining there? Yeah. Okay. I can just put this to get rid of the warning, even though that's maybe not so good. But anyway. Right. And now I have a function that where there's no I/O anywhere. And I can now do these things, for example, simulate pick. So that was the question with do you like static programming and so on. So for example, yes, yes, true, true. And it should, what now? Right, and it results in try Haskell. If I give only one answer, but there are two questions, it gives me nothing. And I could also do the fourth stuff. So are you interested in cars? Do you want it in black? I mean, that would be the easy case. But if I say false there, right, so I can do whatever. I could even do an infinite list here, but then of course the simulation wouldn't stop. Right, and this is like, I love that example. For some reason I always like this idea that you can keep, I mean you have like this one thing, this interaction data type, and you have different interpreters for the same thing. And it's often, it is like this, that you eventually want to run it in I/O, like you want to interact with users, but you also have a pure interpreter that doesn't use any I/O. And that is perfect for unit test, for example. I mean, you could now, test your interactions. Of course, not your interaction function, but like the for and the pick interaction. You could basically debug your interactions without needing I/O, and therefore you could do this like in pure code. And it's often but it's only possible because we separated that. So we had this pure data type interaction, which doesn't mention I/O, and that makes it impossible to do these things like this. Let's see whether I skipped anything. No, I think I did this. Right. So are there any questions at this point? Okay, then I think that's the last chapter, isn't it? Mm-hmm. Yes. So this is just a bit about files. So first of all, there are these simple functions for a whole file. So there's read file, it gets a file path and results in an IO string. So that's the content of the full content of the file. So for example, we have, let's see, we have, I don't know, I never know where exactly I am, but I think I'm in the top level of this IO folder now. So for example, the io.cabal should be available. So I can do read file. Yeah, even in GHI I have like tab completion. And now I hopefully, I mean the string that was returned was the Cabal file, which is, that's some problem I think with my name, because it can't print the German umlaut, so therefore this fails. But I mean that's not because read file failed, it's a problem printing this. Maybe I can take another one, license. Okay, that also contains my name.
Yeah. Change the
or I can just go into source IO, and now it shows the full content of the file. Okay, so that's easy. And we also have write file that I showed before, so we don't have to do that again. So read file, write file. But there's also something called handle-based file I/O. And actually that's more general. I mean, these handles, today we're only talking about file handles, but you also have like the same functions you can use for other handles like sockets and so on. So it's more general. So there are, for a lot of versions of I/O functions that you have already seen that work on the console and with the keyboard, there are versions with a lowercase h in front, and that's then basically the same in the handle case. So as before, we have played a lot with getLine, which reads from the keyboard, and there's an h getLine that gets a handle, for example, a file handle, and then reads a line not from the keyboard but from that file. And we saw this put string line, which prints to the screen, and the h version gets a handle and then prints to whatever that handle handles. And there are also these standard handles, standard in, standard out, standard R. So put string line, the one we've played with, is basically just a special case of h put string line where the handle is standard out. And getLine is just the h getLine where the handle is standard in. So in principle, you wouldn't need you would only need these versions. And there is this is end of file, which says whether you are at the end of a file. And then there is a function. The question, of course, is where do you get your handle from? And there are indeed functions to open a file or close a file and get a handle, but they are not very safe, because if something happens, you open a file explicitly and then something crashes, then it would stay open. Whereas this with file that we are using here takes care of closing it again no matter what. So that has an interesting signature. If you are more experienced in Haskell, this will be second nature, but for you it's maybe a bit complicated at the moment. So it gets a file path, the file you want to work with, then a mode. This is defined here, so there's read mode, write mode, append mode, and read-write mode. It's just an enumeration of these 4 values. And then this interesting argument, so it's a so-called continuation. And then finally result. So what this says is, and when it's executed, it will pass, it will open the file and then pass the handle of that file to this function, which will then result in R, and that's then the overall result of the computation. But you don't have to, if you use this with file function, you don't have to worry about opening the file and closing it again yourself. That's then taken care of by the function. And as an example, we have this read file line by line. So let's try to implement this. So given a file path, it's supposed to return all the lines of the file. I mean, there would be other ways to do this. I mean, you could just use read file and then you have the whole content and then split it into lines. But here we want to use this handle IO just to see an example. Okay, let's go to file. Okay, we use this with file. No, that's wrong, I think. So now it automatically imported this, but we don't want that. We want it from, sorry?
System.io.
Right, thanks. So we want with file, and we also want this IO mode, and we want age getLine, and we want age is end of file. Right. Okay. So where was I? So with file. Okay, it takes the path, the mode, and then the continuation. Right. So the path is file. The mode is read mode, because we just want to read the lines. We don't want to do anything. And now the continuation. So a function that, given the handle, gets us what we want. So let's call the handle. And in IO. So now I can do a do block, and now I do my thing. And I just want to see. Right, and here it's done in a helper function. Sorry. So I mean, I could do it like this. File handle. So I just delegate the real world to a helper function. So now I have a handle, so I must import handle as well, which I can't. Let's see later. Is that also in system.io?
Yeah.
Right. And gives me the list of lines. The reason will become clear why I don't do it inline, why I need this helper function. Okay. Right, so how do I do that? So first I must check whether I'm done. So for that we have this age is end of file. So let's execute that. It takes the handle as argument. So if I'm at the end of file, I'm done. So there are no lines. So I can return the empty list. If, however, I'm not at the end of the file, I need to read one line. So I can use this age get line for the file handle. Now I need to read the rest of the lines, so I can do that recursively. So whatever, other lines. I recursively call read file handle on my handle. And now I can return the first line and the other lines. I'm done. And now I should probably change my name, as much as it pains me. Okay, so now this should work. Okay, read file line by line, io.cabal. At least it didn't crash. Yes, and now we got like a list of strings with all the lines in that Cabal file. So it worked. And was that it? Right, so they are, I mean, we will get to that later. So both of these functions come with certain problems. But for like, especially for trying stuff or for quick and dirty stuff, that's fine, I think. Okay, oh yeah, last topic.
When you need to do
I'm sorry?
in the event read 502
Yeah,
when you need to
sorry, can you the question to this function?
yeah, when you need to
I mean, because, I mean, the type, what's a good answer to that? I mean, I want something of type IO, I mean, I need this too for the same reason I need it here. I mean, I have to return, I mean, in both branches of the if, the type of the result is IO list of string. So, and I mean, one way to produce something in IO is to use a do block. So each time, I'm not sure how I can explain that better. Do you think it's clear?
You don't need the do.
No, I mean, I could of course use bind instead.
Yes.
I mean, it's the same as before. I could use bind. I mean, sorry. I could do, of course, this. I mean, this. I mean, I could write this, of course. I mean, I must write some IO string, and the way to write IO list of strings is using what we have learned. I mean, the primitive operations or whatever, and binding them or sequencing them. And I mean, it's always the case that I can rewrite something like this with the do block. So whenever I have something like this, I can instead use a do block. But yeah. But I mean, maybe the question is, I mean, this do block, I mean, I can't just use do notation without do here. I mean, it's like only on the top level of this thing. I mean, yeah, that's the. Right, are there other questions? Okay. Then last topic in this lecture is exceptions. So if we do this for IO kabl, then I get an exception with file does not exist. And we saw something like that before when I, for example, do undefined. But this, I mean, there is actually a difference. I mean, this undefined or error, that is very bad. So normally you should avoid at all costs that you have pure programs that can have an error. And the problem is the same as in the beginning of this lecture with getLine. I mean, if it had type string, that it's not clear when an exception or in pure code will be triggered, if it will be triggered at all. So for example, we had this lazy nature of the logical OR. So if I, for example, have true or undefined, it will just say true. So the error in the undefined will never be triggered. But even if it will be triggered because of lazy evaluation, it's completely unclear when, or difficult to see when. So it's bad. I mean, exceptions they shouldn't be in pure code. So whenever possible, one should avoid them. But in IO, it's a different story. I mean, first of all, you can't avoid them because in the real, the world is a sad, dangerous place, so a lot of things can go wrong. And secondly, it's less problematic because of this sequencing in IO. This is all that I said just now is no problem in IO. So, it's one step after the other, and if something goes wrong at some point, it's a well-defined point, and we know it will happen at that time. Right. So there are exceptions in IO, and they are like, I can deal with them. So in pure code, one should always, instead of using error, rather do something like maybe, so that you return nothing instead of using error or undefined. But in I/O it's different, it's easier to handle and it's better. And there's, for example, something called catch I/O error. Let's see whether that is indeed there. Yep. So that's indeed there. So, I mean, there are different errors, other errors than I/O errors, but I/O error is like what typically happens, like with file handling stuff. So that's the signature. So what does that mean? The first argument is an I/O action that we want to execute, and we want the A result, but it might potentially throw an I/O exception, something like file does not exist. So the second argument is basically the handler. So if we get an I/O exception, then what result do we want to return then, or what do we do then? So basically, so if all goes well, there's no exception, it will just execute those actions and return the A as final result. If, however, while executing that plan, there is an exception, then this function will be called with the thrown exception as argument. So the outcome is another IOA, and then that is executed instead. Of course, it could, in principle, result in another exception. So that's catch IO error. Now I just want to see, okay. So now we can make our read file line by line. Safer. So let's call it read file line by line prime. And let's change the return type to maybe a list of strings. So the idea is now, if we get an exception, we return nothing. And if we don't get an exception, we return, as before, just the list of lines. And now we can use this catch IO error. So the action we want to execute is almost our old one. But the problem now is it has the wrong return type. So our old one had IO string, list of strings, and now we want IO maybe list of strings. And in this case, if we get our list of strings, that means there was no exception, so it's the good case. So we want to just apply just to the resulting string. And this is exactly what liftm was made for, or fmap. So we can just fmap just over this. Okay, now we must write the handle. So if we get an error, we must say what to do in that case. And in that case, we just want to return nothing. I mean, we could, of course, for example, print the error to the screen first or whatever. So we are not really interested in this, and so we can just do const. And now let's try this again. So first with the file that does exist. So we again get our lines. But now there's a just in front of the list. And now let's do kibble. And we get nothing but no exception. So it's relatively easy to handle these IO exceptions in Haskell. What's this for? Oh, this is just, I'm not sure I need that. I mean, in the slide, it's just another example where first the file exists and then you remove it and then it doesn't exist anymore. And there's only just one new thing that, there's a remove file function that removes files. And it's from system directory. I mean, we don't need it, I think. But of course, it's good to know that there are functions like this. Right. Yeah, but I'm not using that, and I don't want to delete it. I mean, of course, I could create a file. So I could do write file foo text in here. So now I should have here it is. And now I can try out this remove. Hopefully I reload it, of course not. Yeah, exactly. That's good that that happened. I was thinking, I mean, it's not mentioned on the slides, but that's not in the base libraries. That's in a, and actually,
It's in the base, but not in Prelude.
no, but I did, no, it's not in base because I imported it.
Okay.
It's not in base, but it's used by base. I mean, Cabal is aware of it somehow, which is strange, but anyway. But often, if that happens, so could not load module system directly, it's a member of the hidden package directory. So that's if it's a transitive dependency. I mean, if sometimes you use something that Cabal has never heard of, or I mean that nowhere mentioned, then of course it just says doesn't know what it is. But in this case, it seems that one of the libraries that are in scope have a dependency on this one. So in principle, it's like Cabal is aware of it, but I mean, because it's not explicitly exported, you get this error message, but at least you see the name of the package. And now it's an easy matter to just add that, as we learned yesterday, to our build depends in the Cabal file. So all I have to do is add directory. And now reload. And now it works. I mean, now it didn't give an error. No, for some reason I lost my history. Normally you still have them if you restart, but it doesn't matter. Foo text. And now it should be gone. Yeah, okay. So that works. Yeah, I just wanted to demonstrate again how you can, if something's missing, that you can modify your Cabal file and then when you have it available.
Should we, the next is the last slide. Should we tell them about how to compile an executable? Yesterday we didn't.
Yes, I mean, you mean with Cabal install or?
Yeah, Cabal build, Cabal. Yeah, or just.
I mean, I did in the beginning show Cabal run, but yes, sure.
If there wasn't an executable and then run it.
I'm sorry? No, I did show how to run an executable with Cabal run.
But no, yeah, but and the actual executable.
Yes. With Cabal, you mean? Cabal install? Yeah. I just don't want something called I/O floating around on my system. Because it's not so easy to get rid of it again, is it?
Just remove Cabal.
Really? I'm not, maybe. I never know how to. Anyway, let's rename this executable to. Yeah, let's just have some fun. No, it's fine. I can call it whatever. It doesn't matter.
Or maybe just with GIC and.
I don't know how to do that. Okay. I mean, you can of course use GHC directly to create executables, but I never do that. Whatever, Kenya IO or something. Doesn't matter. Right, and let's just, because at the moment it's totally boring, this may, and just Prince Hello Haskell, let's at least use this thing. So import IO, it's maybe an unfortunate name, but why is, okay. It's strange. Just a second. Okay, now it worked, right? It was some whatever. Sometimes you have to, when you change dependencies or so, you have to reload and then all the problems go away. Right. But it's not in this case, it seems. I'll do this again. It is called IO, right? It's called IO. And I am the library, library is called IO. It's exposed.
Oh, the executable doesn't know. Oh, yeah, yeah, yes.
No, I think everything
Yeah,
is.
yeah,
And Cabal also doesn't. Let me just make this bigger. So there just complains that it's done because I'm not using anything, but everything seems to work. I mean, it's a bit strange.
Files,
It's some problem with the editor. Maybe because there is no none of these because I use Cabal. Yeah, I know now. If we look at some of the other examples that I did, sorry. For example, 03. There is this. I mean, this one I created with Cabal init, and the others I created with my tried and proven method of copying something existent. And there is this hi or he YAML file, and that is very. I mean, it has very simple. I mean, it's very short.
Can you zoom in?
Yes. It just says Cradle Cabal. And that is somehow needed for HLS, for the language server, to figure out your project. So let me just copy that into today's folder. And now, hopefully, everything should be fine. Yes. Okay. So that was it. So for whatever reason, this language server, the HLS, which does all the editor support here with these pop-ups, needs to know about the parts of your program, the libraries and so on. And so it needs to know that somehow it should check the Cabal file for that information. And this Cradle Cabal somehow tells it where to find stuff. Right, I wanted to do this read file line by line prime, maybe, and just demonstrating how one would use that. Oh yeah, and there's one thing. So let's say we want an executable that takes as command line parameter I'm not sure how fancy I'm supposed to. I mean, it doesn't matter, but let at least take one command line parameter, the name of the file. We haven't learned yet how to read command line parameters, but let me tell you, there is something called system.environment, and that has something called get args, and let me just show you. Cabal REPL, and by the way, I mean, now I have two things in my Cabal file. I mean, I have the library and I have the executable. And if I now just do Cabal REPL, it takes the library. Sometimes it also complains that it doesn't know what to take. But I can, if I now want the executable, I can say Cabal REPL and the name of the executable, which in this case was Kenya IO, and now it takes the executable. So you can point Cabal REPL at each of the so-called stanzas in your, or the parts of, if you had a test suite, you could also put it, or you can have more than one executable, so then you can pick which one you want the REPL in. So now I wanted to show you the type of getArg, so it's of type IO list of strings. So it will give you the list of command line parameters when you call the program as a list of strings. And I mean, let me just do it quick and dirty. I mean, this is not on the slides, but maybe it's nice to have an example. So, I mean, I don't know what yeah, okay, let's do it properly. So let's write a helper function, let's call it pass args or something. which results in IO file path because I need the name of the file. So I ask for the command line parameters, and if it's just one element, exactly one element, then I return that. And otherwise I say put string line expected exactly one command line. Is it called parameter or argument? I never argument. And now the question is, what do I do now? We haven't really talked about no, oh yeah, no, the recursion doesn't work. I mean, you can't change the, but there is something called throw, no, IO error, I think it's called. Isn't there? Let me just, sorry, always forget what that's called. Throw IO. Okay, it's in control exception. Throw IO. Okay, and in order to get, and then I can do IO error or something. Right. Sorry about this. I just want to do this properly. I mean, there were easier ways to have it crash, but is it, I think, user error or IO error? IO error. See, there is an IO error. Just 1 second. We just do undefined quickly. Very needy. So IO error. So I don't want that really. I mean, I could use IO error instead of, but I need an IO error and user error. Error is what I want. User error and IO error in combination I can use. So I can say IO error. So actually I can do this here. IO error. Like so. So and then I also don't need to do like this. Okay, fine. And now I can use this here. Pass args. And now I can do my maybe lines. Is this read file line by line? And now, I don't know, I can just, for example, print it. And we haven't seen print yet. So print, I mean, we can ask for the type of print, and that takes an arbitrary A which is showable, and then is an IO action. So what it does is just a concatenation of put string line and show. So for example, I can do print true, and it will show true, which is the string true, and then put it on the screen. So this, for example, now, so yeah, I just wanted to, because you asked for how to install it, so I wanted an example of a program. And also, I don't need this. And I wanted to also demonstrate how you normally the library is the thing that contains all the stuff. And the actual executable is normally very short and just imports everything it needs from the library, and it's just like one, I mean, very simple. Main is normally very simple. So now and I use this, and so this get args, as I said, reads the command line parameters, and we want exactly 1, so I wrote this helper function that gets all of them, and if it's exactly 1, then it returns that, but if it's not exactly 1, it throws an exception. So we haven't talked about throwing exceptions yet, but this is one way in I/O to throw exceptions. And then I use this in my main to get the file name from the command line, and then I use the function we defined just now, and I just, I mean, this is of course not very useful program, but I just print it to the screen. And now we can try this. So first, what I showed you before, Cabal, I mean, first we can do a Cabal build to see whether it compiles. And now I showed you before Cabal run, Kenya IO, but this should now, okay. I mean, you can pass parameters also when you use Cabal run, but I think you should use this minus minus, and now you can use the command line parameters. So if I now do io.cabal, for example, then it works and it prints that on the screen, I mean, like this. And if I, for example, don't give a command line parameter, then it crashes and it gives us, I mean, the error message I specified. So this all works. But now, the reason I'm doing all of this was because I wanted to show what, if you really want an executable in your operating system, then you can do Cabal instead of Cabal run, Cabal install, and have a coffee. Although in this case, it won't take that long. Okay, and now it's in my, it's somewhere, and that path is in my path variable, so this is automatically reachable. So now it's just a program like any other on my machine. So now I can do Kenya IO, IO Cabal, for example. And so this is now an honest to God executable without needing Cabal or anything anymore. Right, I think that's it for this. And it's luckily quite early, so we can do the test. But probably we should have, oh yeah, there's one slide, just what we did today. So we talked about I/O, that it marks like parts of your program that potentially have side effects. How to compose I/O functions to bigger functions. We talked about higher order I/O functions, sequence and map M. We talked about how to work with files and resources. I mean, that's also with the handles, and a bit about exceptions. Yes, and showed an example of how to try to keep the pure parts of a program apart from the I/O stuff in this interaction example. Okay, are there any questions? Okay, yes?
On the writing a file, how can you update a file as well?
Then you must open it in read-write mode, I suppose. And I think I've never done that.
Yes, if you open read-write, you have access both to read and write, so you can read it, update in memory, and then write it. Or the other option is to write it a bunch of times.
But I mean, can you also, of course, the simple one would be to use read file to read it in memory, then do something in memory, and then use write file to write the new version. But I think you can also really use read-write mode. So you read until you reach the spot where you are, and then you write into the file directly, and so probably you can use both then. H get line and H put string on the same file handle if you open it in read-write mode. Okay, other questions? Okay, then let's say 10 minutes or 15 minutes break, and then we do the test.
How much?
What, the break? Or?
Yeah, the break.
I don't know, when is the food coming?
Not yet.
So, the test, we thought we should give them an hour for the test? No.
Yeah.
So
Maybe 10 minutes?
10 minutes, and then?
Just also for people that are not here, so they know when the test starts.
Yes, sure. 10 minutes.
this.
Mhm.
Okay, yeah.
Okay, I just want to switch myself off.
Okay, guys, are you ready? So the test will be same as all the exercises we've been doing so far. I just published. It's in the repo. In today's day, there will be a link called T1 Test 1. You click there. It will open the same repository as always. You can still use your local development, Gitpod, VS Code remotely. And the deadline is in exactly 1 hour from now, and 2 minutes. So you can get started, and if there's any issue, let me know. Remember that to check if you're doing the right thing, you can run Cabal test every time to make sure that everything is working. Okay, I think, yeah, that's it. And once the deadline reaches, they will no longer be able to push commits. To
5 minutes before, so we can say
yeah,
they must push what they have.
yeah. Yeah.
Is it this acid stroke one?
First test, yes.
Oh, yeah.
Yeah, perfect.